In our high-power world, there are these invisible guardians working around the clock to keep us safe from electrical catastrophe. Today, we're going to pull back the curtain on one of the most important ones, the unseen protector that stands between us and total disaster.
I mean, really think about that for a second. In factories, huge commercial buildings, and massive power systems, something's got to be the last line of defense, right? Well, the answer is a device you've probably never thought about, but it's always on watch, ready to act in a fraction of a second.
So, to really understand our hero, first we have to meet the villains. On one side, you've got overloads. Think of this as a slow, creeping danger, kind of like running way too many things on one circuit for too long. It's this gradual, dangerous heat buildup. And then, on the other side, you've got short circuits. This is the big one, the explosive, sudden danger. A violent, massive surge of electricity that can literally vaporize metal in an instant. Two totally different threats, but they both need one very clever solution.
So, that's the problem, isn't it? How in the world do you design a single device that can intelligently tell the difference between a slow burn threat and a lightning-fast one? This is the current conundrum that engineers had to solve.
And here it is, the brilliant solution. Everybody, meet the molded case circuit breaker, or as we call it, the MCCB. This is the unsung hero you'll find in electrical panels everywhere, and it's built specifically to handle that dual threat.
So what is this thing exactly? Well, at its core, an MCCB is just an automatic switch. Its entire job is to watch the current, and the second it detects one of those abnormal conditions, the overload or the short circuit, it physically smacks a switch open and interrupts the flow of electricity. And that molded case part, that's super important. It's a tough, insulated housing that keeps all that powerful action safely contained.
Okay, so how does one little box pull off this dual protection mission? Well, it's not with one single mechanism. It's actually a really clever combo of two different systems working together. You could call it a tale of two triggers.
But before we get to those triggers, we have to meet the command center, the trip unit. This is the brain of the whole operation. This is the part that's constantly sensing the electrical current, and when it sees something's wrong, it's the one that yells, "Shut it down." For that slow burn overload problem, the MCCB uses what's called a thermal trip. Inside, there's this really cool little part called a bimetallic strip. It's just two different metals stuck together. As a long sustained overcurrent heats them up, one metal expands more than the other, and that makes the whole strip bend. Think of it like a slow, deliberate thermostat. Once it bends far enough, click, it physically trips a switch. And it has a built-in time delay, so it won't trip for just a harmless little power spike. Pretty smart.
But for a crazy, violent short circuit, you don't have time for something to slowly heat up. You need instant action. And that's where the magnetic trip comes in. A huge surge of current creates this powerful magnetic field inside a coil, which instantly yanks a small plunger. This isn't a slow bend, it's a snap. It's like a mousetrap. It triggers the mechanism immediately, cutting the power before catastrophic damage can happen.
But here's a question. What happens when this contacts snap open under that much power? The electricity doesn't just stop. It can form a super dangerous, high-temperature arc, basically a bolt of lightning inside the breaker. To deal with that, the MCCB shoves that arc into a special chamber called an arc chute, which splits it, cools it, and safely snuffs it out. Now, not all electrical loads are created equal, right? A giant motor has way different needs than, say, a server room, and that means MCCBs can't be a one-size-fits-all solution. You've got to pick the right breaker for the job.
Okay, so your standard workhorse is the thermomagnetic type we've just been talking about. But for more advanced stuff, you have electronic trip units. These use a little microprocessor for incredible precision, and you can actually fine-tune the protection settings. And then you get application-specific types, with tripping curves tailored for really unique loads, like a Type D breaker that can handle the massive startup current of a big motor without tripping by mistake.
So where can you find these things? Oh, they're everywhere high power is being used. They're in the main distribution boards of factories and office buildings. They're dedicated to protecting huge motors. They are absolutely essential for backup generator systems. Even specialized gear like welding machines and capacitor banks, they all rely on MCCBs.
But here's the thing. Like any guardian, an MCCB is only good if it's ready to act when it's needed. You can't just install it and forget it for 20 years. It needs an essential health check. And the key word here is reliability. I mean, this device might sit on a wall for years doing nothing, but it has to work perfectly in the 1 millisecond that it's needed.
That's why a regular testing schedule isn't just a good idea, it's absolutely critical for safety. When it comes to testing that trip unit, there are two main ways to go. Primary injection is the full system workout. Testers pump actual high-power current right through the breaker to make sure the entire chain of events works just like it's supposed to. Secondary injection, on the other hand, is more like a targeted brain scan. It connects right to the electronic trip unit to test its logic and response without having to send those massive currents through the whole circuit.
And just to give you a sense of scale here, some common MCCBs are rated to handle up to 2,500 amps. I mean, that is a staggering amount of power, easily enough to run a small factory or a big office building. And this one device is designed to safely cut that flow in the blink of an eye.
So at the end of the day, it all comes back to this one simple, elegant function. It's an automatic switch that interrupts the current flow during abnormal conditions. It's such a simple concept, but it protects billions of dollars of equipment and, more importantly, countless lives every single day. The MCCB really is a masterpiece of engineering, working silently in the dark. It kind of makes you wonder, doesn't it? What other invisible systems, what other unsung heroes of engineering are out there protecting you every single day? It's something to think about. Thanks for joining me for this one.